Good morning, students. Hello, how are you? I hope you are doing well. So, in our previous lecture, we have discussed about the filling of the orbitals. So, I have told you that the filling of the orbitals will take place in the three ways, and we have gone through our first topic, that is known as Aufbau's principle. So, for filling the orbital, basically we have three methods. It means for filling of orbital, we have basically three methods. Among these three methods, we have our first method, that is Aufbau's principle. Second method we have Pauli's exclusion principle. And the third category we have, that is Hund's rule of maximum multiplicity. Hund's rule of maximum multiplicity. So, here are the three basic methods for filling the orbitals of the energy in any subshell. So, we have gone through our first topic, that is Aufbau's principle. Aufbau is a German word that basically means that building up. So, in the first principle, what we have discussed the orbitals are filled according to the increasing order of their energy. It means the electron will, with lowest energy, will occupy the lowest shell of an atom. So, we have gone through Aufbau's principle. Now, we are on our second topic, that is Pauli's exclusion principle. So, what will be the statement for Pauli's exclusion principle? Pauli's exclusion principle state that no two electrons in an atom or orbital can accommodate more than two atoms, and both the electrons that are present in any shell will have the opposite spins. So, what is the Pauli's exclusion principle? It basically states that orbital can accommodate cannot accommodate more than two electrons, and the electrons which are present must have the opposite spins. So, the two electrons must have opposite spins. So, this is the actual statements for Pauli's exclusion principle, that an orbital cannot accommodate more than two electrons, and if the two electrons are present, their spins must be opposite. So, it is the main idea of Pauli's exclusion principle, and I am showing you with the help of an example. So, what we have seen here, suppose we have orbital 1s and 2s. Now, what I want to do, I want to fill the electrons in this orbital. So, what I have to do, I have to fill the electrons maximum capability of 2, and the two electrons must be present in the opposite spin. So, what we are seeing here, it contains two electrons, and both these electrons have opposite spin, that is one in the clockwise direction and one in the anti-clockwise direction. So, it will show clockwise and anti-clockwise spin. So, this is the main idea of Pauli's exclusion principle, that we have fill only two electrons in the orbital and both the electrons will have only opposite spin. Now, after discussing of Aufbau's principle and Pauli's exclusion principle, we are on our third topic, that is Hund's rule of maximum multiplicity. So we have our third topic, Hund's rule of maximum multiplicity. So what Hund's rule of maximum multiplicity will determine? Hund's rule states that if there is an electron in the orbital, then the electron with same equivalent energy levels cannot be filled in an orbital, and both the electrons that are present must have the opposite spin that Pauli's exclusion principle will have said, but the orbital must contain at least one electron, and if they have the equivalent energy, the spins will be the parallel to each other. So what is the statement for Hund's rule of maximum multiplicity? In an orbital, there must be at least one electron in a subshell. There must be one electron in a subshell, and orbitals having equivalent energy must have parallel spins. Must have parallel spin. So this is the basic statement for the Hund's rule of maximum multiplicity, that it actually states that for filling of an orbital there must be one electron available, and if we have the electrons with equivalent energy, then the spins must be in the parallel spins. Now we will understand this with the help of an example. So we have an example for Hund's rule. Suppose we are given with 3 orbitals. Now what we recognize here, suppose this orbital is 1s, this is 2s, and this is 2p. Now I want to fill the electrons in the orbital. So what I will do, I will fill the 2 electrons in 1s orbital that are of the opposite spin. Now we will have a 2 electrons in 2s that are also of opposite spin. Now we will fill the electrons in the orbital like this. So if I fill the electrons in this manner, so this will be a wrong interpretation according to the Hund's rule of maximum multiplicity, because the last orbital which have equivalent energies are not parallel to each other. So this is basically the wrong method for filling the orbitals. Now what will be the right method according to Hund's rule? Suppose we have again 3 orbitals, 1s, 2s, and the third is 2p. So this orbital is 1s, this is 2s, and in 2p we have the 3 components, that is 2px, py, and pz. These are actually the 3 components of the 2p system. Now what we will do, we will fill the electrons in the orbital. So again we have in 1s orbital there are 2 electrons, in 2s electron there are again 2 electrons, but if I want to fill 2p category, I want one electron in each case, and they must have the parallel spins. So what we will do, one in this, and one in third shell, and what we have seen here, these 3 have the parallel spins. So this is in accordance with the Hund's rule of maximum multiplicity, and this is a right manner to write any configuration. So it is all about the 3 principles, that is Aufbau's principle, second Pauli's exclusion principle, and the third principle we have discussed is Hund's rule of maximum multiplicity. We have one more rule that is called N plus L rule, and it is somewhat similar to that of the Aufbau's principle. So now we will discuss our fourth topic, that is N plus L rule. So what does N plus L rule states that N plus L rule means electrons are filled according to N plus L. It means increasing order of their energy, increasing order of their N number. So N plus rule states that electrons are filled according to N plus L. It means increasing order of energies. So this will be the basic statement for N plus L rule, that electrons are filled according to N plus L statement and increasing order of their energies. So this is in accordance with N plus L rule and it is somewhat similar to that of the Bose principle. Now we will write the electronic configuration of certain elements, so it must be clear to you that which electron will be fitted in which subshell. If someone wants to copy it, please copy it now. Now, in accordance with Bose principle, what we have seen that we have 1s orbital in the first, then we have 2s and 2p, next we have 3s, 3p and 3d, next we have 4s, 4p, 4d and 4f, 5s, 5p, 5d and last we have 6s and 6p. So these are the orbitals according to the Bose principle, in which the electron with the lowest energy will occupy the shell. Now what will happen here? The electron will with lowest energy will occupy the shell. So firstly the electron will fit in the 1s orbital, then in the 2s orbital, then it will occupy 2p and 3s, then 3p and 4s, next 3d, 4p and 5s, then 6s, 5p and 4d and lastly this orbital. So this will be the method of filling the orbitals in accordance with the energy. Now we will learn about some of the elements and write their electronic configuration. So I am discussing the electronic configuration of elements. Electronic configuration of elements from atomic number 1 to 30. So we will write the electronic configuration from atomic number 1 to 30. So again we have three categories here. Firstly we will write atomic number, name of the element and the third column will be the electronic configuration. So firstly we have atomic number. Second category we have name of element and thirdly we have electronic configuration of that element. Now starting from our atomic number 1, we know that atomic number 1 is for hydrogen. So I am writing 10 elements here from 1 to 10. So we have atomic number 1, 2, 3, 4, 5, 6 and 7. For atomic number 1, we have hydrogen. Atomic number 2 is for helium. Atomic number 3 is for lithium. Atomic number 4 is for beryllium. Fifth atomic number is for boron. For 6 we have carbon. And the 7th atomic number is for nitrogen. So we will write nitrogen here. For atomic number 7, I will write from here. Here we have atomic number. Here we will write electronic configuration. So first number is for hydrogen. Now we will write the electronic configuration for this element. As its atomic number is 1, it must contain 1 electron and 1 proton in its nuclei. So its electronic configuration is, firstly the electron will fill in the 1s orbital. So its electronic configuration will be 1s1. Now for helium we have atomic number 2. So its electronic configuration will be 1s2. Now considering the third case lithium, we have only 2 electrons in the s shell. So its electronic configuration will be 1s2, 2s1. Now we have fourth atomic number, that is beryllium. Beryllium we have atomic number 4. Now with atomic number 4, that is for beryllium, we have 4 electrons. So its electronic configuration can be written as 1s2, 2s2. So 2 plus 2 will give the 4, that will be the atomic number of the element. Now we have the fifth element, that is boron. Boron with atomic number 5, the electronic configuration will be 1s2, 2s2. Now the electron will accommodate in the p shell and the electronic configuration will be 1s2, 2s2, 2p1. So 2p1, it will have 5 electrons. Now the sixth element is carbon. Carbon is having atomic number 6. So electronic configuration will be 1s2, 2s2 and 2p2. So these are the electronic configuration of some of the elements according to the Aufbau's principle. Now we are writing certain more elements, as this is the similar from atomic number 1 to 10. Now I am starting from atomic number 11. So we have atomic number 11 and the atomic number 11 is for sodium. If I talk about atomic number 12, 13, 14 and 15, for atomic number 12, after sodium we have aluminium, sodium, magnesium and aluminium. Aluminium, 14 silicon and the 15 one is phosphorus. Now I want to write the electronic configuration from atomic number 11 to 15. So what we will do, we will have a 11 number for sodium, 12 for magnesium, 13 for aluminium, 14 for silicon, and the 15 atomic number will be for the phosphorus. Now for the sodium, atomic number is 11, so we can write the electronic configuration as 1s2, 2s2, 2p6. So look at here, after 2p6 the electron will be accommodated in 3s shell. So 1s2, 2s2, 2p6 and the electronic configuration will be 3s1. Now how will we check the electronic configuration? See here, 6 plus 2 8, 8 plus 2 10 and 10 plus 1 give us 11. So it will be the number of electrons in the particular shell. Similarly for magnesium we can write 1s2, 2s2, 2p6 and 3s2, 1s2, 2s2, 2p6, 3s2. Now see here, for aluminium we have 6 plus 2 8, 8 plus 2 10 and 10 plus 2 12. We are left with the 1 electron. So after 2p and 3s we will fill the orbital, that is 3p. So 1s2, 2s2, 2p6, 3s2 and 3p 1. Now for 14 we have 1s2, 2s2, 2p6, 3s2, 3p 2, 1s2, 2s2, 2p6, 3s2 and 3p 3. So this will be the electronic configuration from the element number 11 to 15 that we have studied. Now we will write the electronic configuration of some more elements. If someone wants to copy it, please copy it now. So now we are going to write about the elements and their atomic number. So we will write from atomic number 21 to 30, which is quite strange from all these. So it is quite easy to learn the atomic number from 1 to 20, but from 21 to 30 it becomes difficult to learn the electronic configuration. So how will we write the electronic configuration from atomic number 21 to 30? So there is a one simple step to learn this formula. We have 21 to 30 elements from the periodic table, and there is a simple formula to learn this table, that is Sc, tellurium, chromium, manganese, Fe, okay. Now this is a simple formula for learning this step, that is scooter TV karo mana fir koi nahi kamzor. So it is a simple syntax to learn the elements from atomic number 21 to 30, that is scooter TV करो मना फिर कोई नहीं कमजोर. So this will be the simple formula to learn the elements from atomic number 21 to 30 in the periodic table. Here scooter is for Sc, that will be the scandium, Ti is for tellurium, V for vanadium, chromium, manganese, iron, copper, nickel and zinc. So this is a simple syntax to learn this formula. Now we will write the electronic configurations from atomic number 21 to 30. Now we have atomic number 21 and the element is scandium. So we will learn from 21, 22, 23 and 24, and the rest of the metals will have the same electronic configuration, only the outermost electron will going to change. So we have first element, that is scandium, tellurium, chromium. Now Sc will be the scandium and having atomic number 21, so its electronic configuration will be 1s2, 2s2, 2p6, 3s2, 3p6 and 4s. So now after filling 1s, 2s, 2p, 3s, we are left with 3p and 4s. So how the electronic configuration can be written? See here, 2 plus 2 4, 4 plus 6 10, 10 plus 2 12, 12 plus 6 18. Now we are left with only 3 electrons. So how will be the orbitals filled? It can be filled in, we have 4s2 in the 1 electron. Now again we have 6 plus 2 8, 8 plus 2 10, 12, 18 and 20. Now we are left with only 1 electron. So 1 electron will occupy the shell, that will be 3d. So it will be 3d1. Similarly, we can write the configuration of the elements in the similar manner, and we have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d2, and the electron will go on increasing in the similar way in like 3d3 and 3d4. So electronic configuration will be same up to this, and after this it will be increasing in the d shell, because the d shell can accommodate maximum of 18 electrons. So this is all about the electronic configuration of some of the elements that we have discussed according to the Aufbau's principle. Now we are on the last topic of our chapter, that what are half filled and fully filled orbitals. So our next topic is half filled and fully filled. So what are half filled and fully filled orbitals? Half filled orbitals and fully filled orbitals have a greater stability according to their exchange energy. It means half filled and fully filled orbitals are greatly stable. How they are stable? Because the electrons in the orbital are half filled or fully filled, they acquire more charge and they are completely stable and they do not need to exchange energy or electrons from each other. So I am considering an example to show the half filled and fully filled electron. So we have taken an example for copper. From this sequence, the copper will have atomic number 21, 22, 23, 24, 25, 26, 27. So copper will be on the 27th number. So we have a series of elements from atomic number 21 to 30. Now we will see the half filled stability and fully filled stability of the atom. So we have considered at atomic number 29. Atomic number 29 is for copper and the symbol for copper is Cu. Now how will we write the electronic configuration of that element? We can write 1s2, 2s2, 2p6, 3s2, 3p6, 4s2 and 3d, 6, 2, 8, 2, 10, 10 plus 8, 18, 18 plus 2, 20. Now what we want to do, we have to write the atomic number for copper, that is 29. So if I write 9 over here, its electronic configuration will be this. Now what we want to do, we will modify the electronic configuration because we want the half filled stability of the atom, because if we have the 10 correct atomicity, then it may be 5 for completely half filled orbital. So we can write the electronic configuration as 1s2, 2s2, 2p6, 3s2, 3p6, 4s1 and 3d 10. So why I write 3d 10? Because on becoming 3d 10, its stability will be the half filled stability. So we can modify certain elements to make them half filled or fully filled, so that their exchange energy will remain stable. So the electronic configuration that is considered for copper will be this. So it is all about the structure of atom. Today we have gone through a lot of topics like Aufbau's principle, Pauli's exclusion principle, Hund's rule, and writing the electronic configuration of certain elements. So this chapter of your chemistry has been completed. I hope you all have learned something from it, and our extra questions will be done in the next session. Thank you so much and have a nice day.